Okay, we will have a quick recap on what we have learned last week. So last week we learned that a spring, okay, either a horizontal one or a spring which is a vertical one, okay, can all be described by Hooke's law. Okay, so showing it with the force F. Okay. Okay, this force is the weight. This force could be anything. Okay, you could learn that the extension here, this is a tip force displacement is equal to the force divided by K. So you can write the external force is equal to the spring force, and it's equal to the Ku. U is the displacement here. Here you will have written the tip displacement in terms of the coordinate y or coordinate b. So you can write this external force is equal likewise equal to the spring force is equal to Kb. Okay. So this is what you learn from the Hooke's law, but from the viewpoint of finite element, so you care about modal forces. Okay, this is on your mechanics. It's about your statics. So you require you no idea about the matrix analysis. Okay, you are simply do this. Okay, this equation. Okay, but how do you write the equation if you're going to have the model analysis? Okay, so let's see. What's your first finite element? So in first finite element, as you can see here, okay. So your first finite element is a force balance at each node. Okay, you're going to write the equation. Okay, by doing the force summation. Take for example, on the two sides of the spring, okay, let's say the horizontal spring, you have the force on the right hand side, and you have the reaction force on the left hand side. You know that how much you pull is equal to how much reaction force. Okay, this is what is common if you are doing the static analysis. But in this case, rather than taking the free body, okay, what is free body? Free body is you take the spring as a rigid body. There's a force P, there's a force R. You previously know that if there is no acceleration, the force sum, okay, must be equal to 0. The force P here is positive because it's along the coordinate x. The force reaction is negative. This is what you learned before. Okay. So, but we don't want this to be changing every time when you handle an element. So instead of looking at the free body, we now focus only on the nodes. Okay. So if you make the cut on the right nodes, okay, what is replaced by the replacement is the spring force. Okay? So if you write these still 0. Force P positive because it's along the x. The spring force, internal spring force is negative. Okay, because it's opposite to the x direction. Likewise, if you are analyzing the nodes 2, okay, you do the same. When you make a cut on the nodes 1, so this part of the spring force is replaced by the forward spring force. Okay, so now you have the forward spring force being positive minus this. Okay, so this is a recap. So once you write the expression of the spring force, you can now write these equations. So means for a spring, when you fill it up, the equation is so now what do we do? We now do transitions. So by writing the force sum, there are two equations. Not 1, not 2. There are force P, there are force negative R. Okay, if you now define the displacement U1 forward, U2 forward. Imagine if you stand on U1, if you really move forward, your reaction force, your spring force will be K U1 minus U2. And now, if you move really pulling the right nodes forward, your spring force will be K U2 minus U1. Okay, this is by doing the shift of the standing. If you stand on the right node and you now shift the stand to node 2, to that node, you're going to express the spring force expressions. Okay? So now, by doing the force sums on node 1, okay, you have minus R plus K U1 minus U2 0. Force sum on the node 2, you have P, okay, and then, okay, sorry, this one should be spring force always negative. Okay, for example. And eventually, you are able to write the thrust equation or spring equation. Okay, if you now do the re-expressions, okay, K U1 minus K U2 is equal to minus R, and then your this K U1 plus K U2 equal to P. So now we re-express them as the matrix form. Right hand side is the force vector. Okay, left hand side is the displacement vector times the matrix. And we call this matrix is the stiffness matrix. Okay? I think you should go back and try how to apply this. Okay, this is basic. And then in the last part of the class, what do you do? Okay, there are no handling horizontal spring. This is the equation for horizontal spring. Okay, a horizontal spring, you define it with displacement U1, U2. But what happens to the spring which is inclined? If it's inclined to the horizontal, then you define this displacement big U1, big E1, big U1, big U2, big 2. But if this is the spring, the same spring, are we going to write the same equation? The equation remains valid. Okay. But now you realize that the coordinate is going to be change. What this equation is written for. To be precise, this is not displacement. This is the axial elongations on the end nodes. Okay? Yeah. So you might find that, why do we need to go through all this? Okay? Because eventually you see that if you really go through this, so you can handle the combination of any matrices. Remember how do we analyze the swing back? Okay? How do you analyze the swing back? Okay? Yeah. So if you want to analyze this, you every time have to draw. Okay, but can we do the standardization of the spring force analysis if there is an inclination? Okay? Or you want to change this to be theta, that's also fine. If you change this to theta, this angle will be 180 degrees minus 2 theta. Okay? So how to rewrite this equation? Okay? So let me try it out again. So it will take you some time, but after that, then you're going to make this template. Okay? So remember, this is what you call the truss equation. Every time when you look at the element, if it is a horizontal spring or if it's a vertical spring, you can write this equation. But what happens if you have the inclined rod? Okay? If you have inclined rod, you can't write it there. Okay? But never mind. You know that the basic idea is if you have the elongation. Okay? This is what we call axial elongation. We know the form of equation is like that. What happens if you now have the inclined one? Okay? The inclinations doesn't make the change. Okay? Remember your tip displacement. Okay? If your tip displacement is combined, okay, you're going to have U1, V1. Okay? They are going to be combined to be a vector here. Okay? This vector need not be aligned to the axis. Okay? This is the total displacement at not 1. Okay? It need not be aligned to the spring. Okay? But in this case, our equation here is axial elongation. I only want the axial component. How can I write the axial component here? Okay? So if that's the case, the axial component is going to be the sum of big U1, okay, projected onto this line. Okay? If you now do the projection, I have this. This part is big U1 cosine theta. How about this big V1? Big V1, you know if this angle is theta, the opposite angle is also theta. So the projection of the vertical displacement onto the spring axis is now V1 sine theta. Okay? The same apply also on second node. The second node has V1, V2, U2, V2. Then you also write the big U2 cosine theta plus big V2 sine theta. Okay? So you will now write the equation. Your U1, U2 into the matrix form. Okay? You can express this. You can express this as sine something times u1 d1 u2 d2. And what is this something? This something you define. Okay, this is 4 by 1 vector. This must be 2 by 4 matrix. Okay? So, where is the first step of your computational procedure? The first step of any computation procedure is convert your multiplications and sum into the matrix form. I know this is the multiplication of u1 cosine theta. I know this is the multiplication of e1 cosine theta. But I want to express them into the matrix vector multiplication. So this is where I have u1 up here times cosine. Let's put cosine to be c, okay, and sine to be x. So the first one is cosine sine. Then multiply u2 b2. No, it doesn't. It's 0 0. And then second, then you convert u2. U2 is has nothing to do with u1 b1, but it has a sum of u2 cosine and b2 sine. Okay? So in that way, let's write the equation over here. So how is the equation changed? The equation now k minus k now times and this matrix. What is this matrix? This is 2 by 2 multiplied by CS 0 0 0 0 CS. This is 2 by 4, and then multiply your big U1, big B1, big U2, big B2 is equal to my force. Okay? So I can generalize it rather than writing reaction and force P. I write this force F1, F2. Okay? This is the external force. Okay? Nothing changed. Okay, but if you look at the operation, you see this. This is 2 by 2, 2 by 4, 4 by 1. And then in the end, the right hand side is 2 by 1 force factor. Okay? So this, does it help? No, it doesn't help. Why it doesn't help? Because your operations are still not generalizing what happened to the inclined rock. Okay? Even though your displacement could have been changed to Cartesian or so-called global coordinate. Okay? This is the axial elongation. Small u1 and small u2 is axial elongation. Okay? But my equation here, this side, what force is it? What force is it? These remain axial forces. This is not the Fx1. This is not the Fy1. This is not Fx2. And this is not Fy2. The force here, okay, I write down the lower thing to distinguish axial from the Cartesian force. Okay? So one thing you find that how could I write the axial force? Okay? If you remember the axial force is net force F1. Okay? Then it becomes easy to do the projection to find what is your Cartesian force. Your F1x is axial F1 times cosine theta. And how about your axial force F1y? Okay, it is basically F1 So the question here, why I only have axial force on this rock? Why aren't there any axial forces? Okay. So if you look at the sling back, okay, look at the sling back. Okay, there's the zip up. So you have support here, I have left sling and right sling. Okay? Why there is only axial force? Why aren't there any perpendicular force? Okay? At the joint. Okay. 为什么你这个吊带只有轴线？它没有垂直力。OK， 同学如果不清楚轴向力跟垂直力，请一下。来，同学来拉一个，来，两位同学示范。You can try to define what is axial force。哎呀，一人抓一点。来，拉，有轴向力吗？什么叫垂直力？啊，你试试看，你试一下垂直力会怎么样？你确定？是你拉一下，也有垂直力。你晚上已经需要克服，你们没拉，拉几千有张力，不要拉断手带。然后，那你垂直力需要用力。When you pull with tension, okay, there is an axial force, okay. But when you now try to lift up your hand, do you feel there is a resistance in the vertical direction? Okay. Why there is no resistance when you move up? Okay. Anyway, this is a cable. There is no bending. If there is no bending, there is no resistance to perpendicular displacement. So this is the nature of cable. Okay. 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 So this is why we can have the assumption for any truss element with the pin support, you can have you don't have any resistance to rotation. Okay? So there are no resistant force. Okay? So as a result, your net force here, you can write here the capital F. Okay, your capital F1 X is equal to F1 cosine theta. Your capital 1Y is F1 sine theta. How about your F2x is F2 cosine theta? How about F2y? It is your F2 sine theta. Okay. Good to get it. So this is for the first nodal force on node 1. How are we going to expand the writing? Okay, if we are going to expand the writing, what we're going to change is changing this from 1%. Okay? So look at the expression of the last equation. K minus K minus K times CS 0, 0, 0, 0 CS times V1, V1, V2, V2 is equal to axial force. This is the global displacement. What is this? This is axial forces. We're not going to do any solution for that because your global displacement in the Cartesian coordinate has nothing to do with the axial forces. Okay? How do you do the shifting? If you're going to solve everything global, okay, the only thing you can do is look at the equation. You can find that if you want to convert F1 V1, you can write this F1x, F1y, F2x, F2y. By referring to the equation here, okay, you know that this equation can be written as 4/1 vector to be expressed in terms of 2/1 vector. You must multiply with some matrix. This matrix is cosine 0. Cosine F1 is 0, F2. And then sine F1, cosine 0. And then later you have 0, cosine F2, 0. And then sine F2. So you 现在做的是什么？我希望我把我右手边的轴向力写成 xy 方向。So in order to do this you need to do the multiplication. C0 S0 0 C0 S. This is what you have to multiply. After your multiplication, your right hand side will become F1x, F1y, F2x, F2y. And then this equation, what happened? You also need to multiply C0S 0 C0S. What this is the transpose of your rotational matrix. Okay? You can see this is the sort of rotational matrix. Okay? So what is the right hand side? You're going to do the multiplication. My right hand side can be written as U, big U1, big U2, big U2, big U2. Okay? If you already express the left hand side in terms of global displacement, and now your right hand side also global forces. Okay, it's no more the axial forces. Then you're going to obtain the full stiffness matrix. In the Cartesian coordinate. Okay. How to obtain this? Okay. Yeah, we can do the multiplication. Okay. Let's see how to do the Okay, we'll show you. We're going to multiply the first two terms. Okay, can it be multiplied? This is 4/2 and 2/2. Doable. Okay, except it is a bit tedious. Okay, so what is end up? Before you do matrix calculation, know the signs first. 4/2, 2/2. So in the end, what do you have? You still have 4/2. Okay, looking at the signs back up this k, okay? So that is 1 minus 1 minus 1, 1, okay? You have first row, first column, you have your C. First row, second column, you have minus C. Second row, first column, you have S. Second row, second column, you have minus S. Third row, first column, you have minus C. First row, second column, you have positive C. Fourth row, first column, you have minus S. And then what do we have next? Fourth row, second column, you have positive S. So this is the first operation for this part. Okay? And then next, I want to complete the multiplication. Okay? I'll take this part, which has already multiplied, and then I'm multiplying with, again I take the k to the last, C, S, 0, 0, and then I'll take k outside also, 0, 0, C, S. Okay? What is this matrix? This is 4 by 2, this is 2 by 4. So what's the size of your N matrix? 2 by 4 times 2 by 4. In the end, you got 4 by 4 matrix. Okay? So let's take the first row. First row, first column, C squared. First row, second column, CS. First row, third column, minus C squared. First row, the fourth column, minus CS. Okay. And next, we're looking at the second row. Second row, first column, you have CS. Second row, and then second column, S squared. Second row, third column, you have minus CS. Second row, and then fourth column, you have minus S squared. Okay, and we continue doing the third row. Third row, first column, you have minus C squared. Third row, second column, you have minus CS. Third row, fourth column, you have positive C squared. Third row, fourth column, you have your CS. And then we come to the fourth row. Fourth row is the CS. Fourth row, first column. Fourth row, second column. Fourth row, third column. Then we have CS. And fourth row, fourth column, we have S squared. Okay. So now I can copy these stiffness matrix. C squared CS minus C squared minus CS, and then times K. Okay, we can put a K 1. Okay, and then this one is CS S squared minus CS minus S squared minus C squared minus CS C squared CS. CS, S squared, CS, S squared. So in the end, what is your new equation? Okay. Look at the thrust equations for horizontal describing the same spring, but because of the inclination, you have to do this transformation. Okay, if you want to see more clearly, the expressions of your trust matrix is positive 1 minus 1 minus 1 1 times k. Okay? So what should you do to check if it is correct or not? 我就跟他讲，你如果这个是一个通用的有限元素，它会属于角对的，那你应该也适用在这个情况。How to describe this equation? Okay, remember this equation? Let's go the checking. I have already spent time deriving the truss equations in the 2D space. Okay? How can I be sure it is right or wrong? Okay? Very simple. What is the difference between the inclined rod as from the horizontal rod? Okay? You know the equation here. A1 is 1, 1 and to describe this you have U1, U2. This is your horizontal equation. But my general equation looks so complex. How am I going to ensure if I'm getting the general equation right? Very simple. Define what is your C. Your C is cosine 0 degree, 0 degree 1. What is your S? S is your sine 0 degree, 0. If I'm going to apply my general equation, I'm going to graph this the same. Okay. So let's do the slide here. So this is cosine squared. So it is 1 squared. Because s is 0, then you have 0. Because this is negative 1 squared. And this is negative 0. And then by doing the substitution, 0. And then 0, 0, minus 0. Then doing the substitution of C and S to the third row, then you have minus 1, 0, also 1, 0. And substitution of the C and S into the last row, then you have 0, 0, 0, 0. So in the end, you see that you have obtained the same equation. How do you read this equation? This equation has only non-zero terms associated with U1 and non-zero term associated with U2. You have axial force associated with U1, U2. And then next, look at the third row. The third row, they have the non-zero term of the stiffness associated with U1, U2. Then the axial force. So this tell you, yeah, my derivation is correct. Because if I do the degeneralization, okay, this is the degenerate form of my horizontal stiffness matrix. Can you see that? So what makes mastering of metrics analysis is difficult. 所以你在写公式的时候，为什么举证写法有点难 ？OK， 它真的太散 ，OK。但是你还是要从手动去自己看一下，怎样从2×2矩阵变成4×4，这个进步矩阵，那4×4还要变成2×2。Okay, so you need to know how to re-express the matrix of stiffness into 4×4 or 4×4 to 2×2, depending on the cases. Okay, so this is the requirement most of you might believe that, or you do try it, you do master that. Okay, forget about your mechanics of material, or forget about your statics. So we're going to use it. Eventually will lead to matrix expression of the stiffness. In later operation, please know how to do the conversion. Okay? So if you're not sure this is the right one, we can do one more practice. Okay? This time round, what are we going to practice? We're going to practice to write the equation for vertical vertical rod, you might find that, oh, nothing. I'm just expressing, changing the coordinate. It is still the same expression. Okay? However, your matrix here got changed in the row coordinate. So in this case, I'm going to rewrite this. Okay, what I'm going to write? Right, U1, V1, U2, V2 is equal to F1x, F1y, F2x, F2y. Okay? And then the right hand side, the displacement vector must be multiplied with the stiffness vector. In this case, the vertical one, this is angle is 90 degrees. Cosine 90 degree is 0. Sine 90 degree is 1. As a result, when you do the substitution back, you're going to have 0, 0, 0, 0, the first row. And next you're going to have the second row, 0, 1, minus 0, minus 1. And the third row of this matrix, you're going to have 0, 0, 0, 0, because they are all multiplied with C. And then in the last row of this matrix, then you're going to have 0, minus 1, 0, 1. Okay? Do you get that equation back? Yes, you have. Why is that the case? Because in this case, the non-zero term is associated with vertical displacement. And in the second row, and in the fourth row. Okay? And then, as a result, you can degenerate a matrix 2 by 2, 4 by 4 into a 2 by 2 matrix. Okay? 所以今天做的只是一个很简单的一个矩阵的一个操作。那你后面你要解题的时候，看看。So this is just a simple operation, reduction of 4 by 4 stiffness matrix into 2 by 2. And then next we're going to show you the practical example. Okay, before I show you the MATLAB operation, I will go through with you the normal operation first. Because in the end, in the first midterm examination, you're going to do a calculation. Even though you're going to have hands-on in the NC sessions and that session, but you still need to master the hand calculation. easier. Okay, now we're going to handle the 2D one. 2D one will also show you how to do hand calculations. But now we're going to do the analysis of the 2D one. Okay, what is structure? Truss structure. This is the simplest truss structure. Okay, later we're going to analyze this. Okay. Okay, where do you see this truss structure? Okay, 哪里有看过这种？这只是一个成分，那我们给你看一下最简单的。就是之前在我们这些 will you find this bracket? Will you find this bracket? Look around. I tell you, where do you find this bracket? Before I can start. 我们分析结构应该知道它哪里的结构。我们是不是派同学去后面窗拍张照，看看那个冷气是用什么架上来？来，说说同学，给我这个光。You see the bracket? 一样吗？一样。Okay, yeah. So later you can go back to the window side to see where do you find this bracket. This bracket is best to support the vertical loading. So if you are not sure where to find this bracket, okay, go to the toilet, look at the basin, okay, at the bottom of the sink, it is always this simple bracket. Okay. If you are not sure this is a nice structure, then we will see what you are doing. Find this bracket. Do you find the bracket? Okay, how do you find? Okay, we pose it. Okay. So what kind of bracket? 你看到没有？你看一条横的绳，那下面这根承压的时候，那就是有双。Okay. So this is how the structure is made. Even though you need not to have the gravity. Yeah, this is a moving structure. Okay, otherwise, yeah. So this is structure number one. Okay, the first structure with the least element. Okay, any truss, three truss make a structure. Okay, this can be part of your leg. This can be part of tension cable. Then you can support the vertical weight. Okay, how to solve this question? Okay, we already know the expression of the 2D truss. Okay. As for summary, I will write it. Next time, this is a 2D truss. You don't need to rewrite the equation again. Okay? But you need to apply them. Okay? We are not going to ask you to do this operation. Okay? Because this operation is quite tedious. What you need to know is you need to know that this is the expression. So this is a 2D truss equation you have to memorize. Okay, many of you might not remember what it is. You have to graphically know the meaning. Okay. What's the expression here? You need to know this. Balance is the x and y coordinate. Next, the good part is most of the students forget is what is the axial force? We'll come back to axial force later. The axial force, remember, you're going to derive the axial elongation and then find the difference of the axial elongation times A, and then you're going to obtain the force. So you're not sure what this is, then you write the equation twice so you can later like this. This is not clear to you, right? Okay, what is the top pass here? Okay, later we'll do the analysis. Okay, now we're going to handling the solution for the first inclined equation. Okay. So previously our coordinate defined here is theta and the apex of the sling. Okay. Okay. Because our rod defined in our derivation is based on the inclination of the rod with respect to the horizontal plane. The current theta here is not the theta I use for the derivation. I should always stick to the same definition of my angle. My angle of inclination is the angle of the rod with respect to the horizontal plane. It is not a rod inclination with respect to the vertical plane. So I should use 90 degree minus theta as the inclination. If that's the case, okay, I am going to solve the deformation of my equation. I have an inclined beam which is inclined by 90 degree minus theta with respect to the angle, with respect to the horizontal plane. On the bottom, on the angle, there are axial force F1, F2. Okay? I can express this axial force into horizontal force. Okay? So previously I am writing F1x, F1y. If you are doing the programming, you won't be afford to find x and y because you only have variable 1, variable 2, variable 3, variable 4. Okay? So sometimes when you read the programming, they write 1, 2, 3, 4 to represent odd number for x, even number for y. Okay? And then on which node you will take the ratio, take the region. Okay? It is 1 over 2, 0, the remainder is 0. Then you define this to be not 1. Okay? Okay, likewise, for unknown displacement U1 B, which I defined previously, to the program, there are no difference between U and B. Whereas displacement variable 1, displacement variable 2, displacement variable 3, and displacement variable 4. Okay, this is the coding and definition based on the program. But for our on-hand calculation, you can still define coordinate x and y, displacement u and b at node 1, or f1 at 2. Okay, so you can do this. In this case, for a sling that supports the weight, how do you describe this physical model? First, they support the weight, okay, by hand supporting the middle. Okay? So the support here, okay, you can see that the top part, it is a pin, it is an anchor, it's not moving. So I can say that node 2 is fixed. So the boundary here will have zero displacement in the x and y directions. And then next, if your back is moving or shaking, okay, then the back are allowed to slide down because of the symmetry. Okay, so that's why in this model you define node 1 is allowed to move up and down, but restrained from moving sideways. In this way, you're going to show that you're going to reduce the question. Okay, let's see. How to do the solution? The solution is very simple. You write down the 2D truss equations. You define where is your boundary. As I told you, node 2 is fixed. If node 2 is fixed, this 2 is 0. Down, then you see. Okay. So beside writing the equation, please write and draw the matrix, the truss element order when you are answering. Okay. You see here, U2 is fixed. So U2 B2. Not 2 is fixed, so you do 2. And then next, B1 is non-zero, but U2 is restrained, and U1 is restrained, so U1 is 0. And then next, what is the force applied? The force applied on this sling is half the weight in the vertical direction, because the weight is pointing downward. It is opposing to my definition of coordinate. My definition of coordinate is x toward the right, y toward upward. So as a result, any force pointing downward is negative. So this is minus F2. Okay. With this, now I can write the equations. Okay, what these equations? So my K, because all other terms are 0 displacement, you can find the reaction force F2x, F2y, and F1x. But the only variable is what? The only variable is V1. So let's take the first, the only variable that happens to be the second row. Then you have the force sum on the second row. And then you have what's the contribution of the internal force? Because all other displacement is 0, then you are only left with Ks2 P1 is equal to minus P over 2. Okay. So as a result, what is the solution here? The solution here is your vertical displacement is P over 2K S squared. It is P over 2K 90 degree minus theta. So this turns out to be cosine. Okay. So your final solution is P P over 2K cosine theta. Okay. Yeah. So rather than attempting your first homework, please go back and rewrite this so that you have a hand how is your calculation done. Okay. So next, we going to analyze the truss bracket. So how does the truss bracket look like? The truss bracket basically consists of a vertical wall, consists of horizontal bars, and an inclined bar. Okay. So in this case, the inclination of the inclined bar in this case will be, I don't know, let's see. How much is the angle? Yeah, it will be 30 degrees. Horizontal bar, the inclination is it 100 degree or 0 degree? It all depends on your. Okay, let's divide 1 each. Okay, for the inclined bar, okay, because we are talking about inclination with respect to the horizontal, this is 30 degree. Okay, the length is, you're going to do the calculation properly. Okay, this is not a difficult bracket, but this is a common bracket. third row is the negative of first row. You see that? And then second row and the third row is the negative of the second row. Okay. 所以你在算的时候，你有没有写错公式？你大概判断一下。Okay, then next, we're asking you the mechanics. Why the first and the third row having the opposite stiffness? 为什么是这两张是正负？好，或者是negative？ So this is for the first and the third is for x direction. The second and the fourth is in the y direction. Okay, then next, how about the signs as well? Depending how you see it. So this is roughly it. Okay, and then next, how do we analyze the bracket? Okay, forget about the bracket. Let's describe the bracket first. In this case, your bracket has not two. No, this is not one. 1, 2. This has a length L. This has the angle 60 degrees with respect to the vertical, angle 30 degrees with respect to the horizontal, and then the horizontal bar has the length of 1. If this is L, then this is L sine 60 degrees. So this is L times square root of 3 divided by 2. So if this is element 1, A1 is equal to EA over L. Okay, this is element 1. If this is element 2, A2 is equal to EA over L over square root of 3 and divided by 3, this is 2A over square root of 3L. Assume the rock, the same section, and you go outside and see what's the bracket look like. You are cutting the rock from the long one. Okay? If the rock is made of the same material, modulus is the same. If the rock is made of the same section, cross-section area is the same. What is different is when you make the bracket, you cut them out different length. What means you cannot see that. And this is the material. I'm going to cut these the length of L for the element 1. This is the same material, I'm cutting it shorter. So this is the length of square root of 3 over 2L. Okay? So this is the way you cut. How about the section? The section will remain the same. We are talking about using the L section bracket. Okay? But most of the time, here we assume simple square bracket. Later in the analysis calculation, we define the section area. Okay, next. How are you going to find what is the T displacement? Okay. If you are loading this structure with the force P, want to know what is the tip displacement. This tip displacement is U2, V2, given the loading at 2y equal to minus p. So that's the question. Okay. So if we're now going to do the solution, let's do one by one. Okay, define the questions. Okay, you can define the coordinate. This is not 1, not 2, and not 3. So here you can say, oh, my displacement here is big U1. This is for element 2. How do you want to define? You can define U3, U2. Okay, this stands the same definition as 3, 2. If you define that, that one is going to be the force in the not 3 and force in not 2. Okay. So the angle for this is 0 degree. Okay. However, if you are defining not 2, 3, the angle here is 180 degree. It doesn't change much, okay? But the sequence is going to be different. Okay. Yeah. And then next, we look at the more complex element. What's the more complex element? We're looking at this inclined beam. For the inclined beam, we are not talking about the angle versus vertical. We are talking about angle versus the horizontal line. This is 30 degree. Okay. Then your cosine 30 degree is square root of 3 over 2. Your cosine, your sine 30 degree is equal to half. So in this way, what is your stiffness matrix? Okay, your stiffness matrix is K times, okay, your what way your not 1? Your not 1 is 1, 2, okay, the same, that's right. V1, V1, V2, V2 is equal to F1x. Okay, we write them the lower case because it is still an internal. F1y, F2x, y. Okay, let's see. Let's do the substitution. In the first row, C is square root of 3. Okay, then you have 3 over 4. And then this one is square root of 3 over 4. This one is minus 3 over 4. This is minus square root of 3 over 4. And then you do the second row calculation. You have the square root of 3 divided by 4. This is a quarter. This is square root of 3 over 4. This is minus a quarter. And then next you do the substitution in the first row. You have minus 3 over 4. Minus square root of 3 over 4. This is 3 over 4. And this is minus square root of 3 over 4. And finally, then you have fourth row. You have square root of 3 over 4. Quarter. Negative. And then you have square root of 3 over 4. And you have quarter. So in this case, are you done with the expressions? Yeah, not so soon. Okay. Usually, I think in the textbook they will ask you, can you do the assembly of two equations? Yeah, you can do that, no problem. But in this case, if you're writing how do you write them? You need to know how to write them. Because currently you have two elements. If you're going to write them full, you're going to write U1, U1, U2, U2, U3, and then F1x, F2x, F1y, F2x, F2y, F3x, F3y. Okay. So you do the shifting of the equation then. So this is too tedious. In the end, you want to find what is U1, this is U2, what is U2 and V2, given the loading, and to Y minus P. So if that's the case, you only have because let's see what is the free nodes, not one. Angle U1 0, E1 0. So this times 0. Next, how about the other boundary? Not 3, U2 0, U3 0. So you already see that they are 0. So this two term is called reaction. The force control reaction. The only free one appear in the third and the fourth row of equation. Okay. And because the rest of the variable displacement are 0. This is going to be first column, second column, and then you only have the third and the fourth column need to be multiplied with unknown U2, V2. Okay? So then let's see where you have U2, V2. U2, V2 from the first element will come from this equation. Okay? You can go and error. You can go and copy them. No problem. So let's copy them. So now copy. You not to forget you are multiplying K1. Okay? This U2, V2, you have element not carrying here. So you have 3 over 4 times K1. Then minus square root of 3 over 4 is 1. And this one is square root of 3. Okay. We go and check the equation. Okay, and finally, let's look at the previous first equation. Where do you have these horizontal? Okay, where do you have this? U3, U2. Your stiffness is K2 minus K2 minus K2, K2, and U3. U2. Okay, where do you have the U2 term? U2 term appear here. So we only need to add one term. One more term. Status K2. Okay. With this, you are able to write the unknowns quarter of A1 plus A2 minus square root of 3 over 4 A1 and square root of 3 over 4 A1 and then a quarter of A1 times Q2 B2 is equal to the force. How much is the force? The force is horizontal force is 0 and then vertical force is minus P. So in this course, yeah, it will be quite tedious. Okay, but you have to first try it once, and later you can do it by method or something simple. Now we can conclude. Yeah, before the invention of the computer, okay, nobody wants to do this. Mechanics, structural analysis do not do this because it's very tedious. Okay, but with the invention of the computer, this becomes something doable. Okay. I think the calculation, yeah, I think not to be corrected. I think this is possible. Yeah, possible. Very good. We'll see. Okay, anyway, in the first equation, you have these part associated with free nodes. In the second equation, you have this part associated with free nodes. You can write them full, but it's going to be very tedious. Okay? Or you can write it short. You just pick up the one associated with free nodes. U3, U4. Okay? And now you only need to solve the equation associated with free nodes. Free displacement. Okay? And this gives you the answer. Okay? With this, to solve for the answer.